Okay, so next talk, Wenda Zhang, modeling X-ray polarization of accretion black holes with Monk. Whatever you want.
Yeah, so good morning, everyone. So first, I would like to thank the organizer for giving me this opportunity to introduce our work. I'm Wenda Zhang from National Astronomical Observatories of the Chinese Academy of Sciences. And today I'm going to talk about modeling X-ray polarizations of accretion black holes with Monk, the GR radiative transfer code we developed in Prague. And the work has been done in collaboration with Michal Dovchak, Michal Busa, Vladimir Karas from Prague, and Giorgio Matt, Francesco Versini from Rome, and more. So we all know that we see thermal X-ray emissions from both AGNs on the left and the black hole expanderies in the hot state in this figure to the right. And in the X-ray band, they show non-thermal emission that can be described by a mainly a power law function, then with the 100 cutoff from like a few tens to hundreds of keV. And I think it's generally accepted that the non-thermal emission from agents and hot state X-ray binaries from the so-called X-ray corona. So the X-ray corona, they contain hot plasma with temperatures from, again, tens to hundreds of keV. And this plasma will inversely condense seed photons from the accretion disk and also from other regions in the case of AGN. Then naturally, for observers, we see power law emission with cutoffs. Well, we know that the hot corona are responsible for the hot X-ray, but there are many things about corona that we don't know yet. For example, what are the geometries of the corona? Are they slab-like, like this one, or are they spherical, like this one, or are they cylinder, like this one? So if you look at the figure on the right, done by Pierre Oliver Petrucci, then you see that if you adjust the optical depth, then the condensed part of the energy spectrum are nearly the same for different geometries. So it means that only by spectral fitting, you cannot tell the geometry of the corona. And another question, are the corona outflowing? So in this paper, Liu et al. 2014, they found out that the C41 galaxies are more luminous than C42 galaxies in the 2 to 10 keV X-ray band. So their interpretation is that because we know C41 is observed at a lower inclination than C42, then because the C41, because the X-ray corona are outflowing, so we see enhanced X-ray emission from C41 than C42. But of course, there are question follows that how to confirm this outflowing corona scenario and how to measure the outflow velocity if this scenario is true. And another question about the black hole is how fast that black hole spinning. And for this particular black hole binary, GROJ1655-40, the spin measurements from different methods, they are not consistent with each other. So from the continuum fitting method, people get a more or less moderate spin around 0.7. And from the broad Ireland fitting method, people found out that there should be a nearly extreme curve black hole. But from the timing method, by fitting the QPO frequency, Malta et al. Found that the spin is quite low, around 0.3. And how are we going to resolve these issues? Like, how are we going to tell the geometry, the outflow velocity, and the spin of the black holes? So probably X-ray polarimetric observations can help, because they will provide us with additional inference about the compact objects, and hopefully this will break degeneracies from the spectral fitting or timing analysis alone. And luckily, in the next few years, there will be two X-ray space missions with high sensitivity X-ray polarimeter that will be launched. There is this XPIE, a NASA mission that will be launched later this year, and the Chinese European mission ESTP that will be launched in around 6 years. So to interpret this data from these polarimetric observations, so we need to model the X-ray polarization. To model the polarization of accreting black holes, we developed this Monk software. It's a general relativistic Monte Carlo radiative transfer code. It's basically retreating the photons along neurogeodesics in curved spacetime and collecting photons arriving at infinity. So at infinity, we can reconstruct the energy spectra, the light curve, and polarization inverse. It includes all GR effects, the redshift, time dilation, light bending, and rotation of the polarization angle. And for opacities, there are Compton scattering, free absorption, and synchrotron self-absorption as well. And in particular, it supports polarized calculation. So it means we can model the polarization. So we did a lot of works with Monk, and for the polarization of accretion black holes, I will introduce these two works. One is the X-ray polarization of black hole observatories in the hard state, and the other one is modeling the X-ray polarization of AGNs. So first, the black hole boundaries in the hard state. So the setups is as follows. We assume either non-spinning or extreme curve black holes with black hole mass of 10 solar masses. And we assume different geometries for the cornea. That we assume spherical cornea, the oblate cornea that are elongated along the vertical direction, and we also assume the conical cornea. And for this conical cornea, we assume stationary ones, and we also model the case where the cornea is moving along the vertical direction, because there were works suggesting that the cornea are outflowing, as I mentioned earlier. So in this case, I just show the polarization of black matter is for one case where the cornea is spherical. So from top to bottom, the energy spectrum, the polarization degree in percentage, and the polarization angle in degree. And from left to right is the increasing observer's inclination. So it's basically face on the left and nearly edge on the rightmost panels. In each figure, the red curve is for the disk, the blue curve is for the corner, and the black one is for the sum of the two. So the most obvious results from this figure is that if you look at the polarization degree, then for both the disk and the corner, their polarization degree increases with the observer's inclination. So you will see more polarized X-ray radiation if you look at the source edge on than face on. And if you look at the polarization angle, especially the polarization angle of the cornea, then they don't change too much. Now, I will show you how the polarization degree changes with various parameters. Here is how the polarization degree changes with the black spin. So again, the upper panel is for the energy spectrum from 0.5 keV to 20 keV, and bottom panel is the polarization degree. So if you look at the energy spectrum, then what do you see? That the spectrum of the coronal emission are nearly with the same shape, and the normalization differs by only a factor of 2. So it's really hard to tell from the energy spectrum. But if you look at the polarization degree, then they are quite different. So the polarization degree of the non-spinning black hole is only around 2%, and the maximum is 3%. But if you look at extreme curved black hole, then it can be as much as 8%. And in the entire energy band, it's more polarized than non-spinning black hole. So it means potentially we can use polarization data to constrain the spin of the black hole. And it's sensitive to the geometry. So here I show again the energy spectrum and the polarization degree for spherical cornea at different heights, and solid is height 5, dashed line is height 10, and the dotted line height 20. And again, the shape of the energy spectrum are almost the same, but the polarization degree increases with the height of the cornea. So it means we can also put constraints on the height of cornea or on the geometry of the cornea with polarization. And it's sensitive to the velocity of the cornea as well. So here I show the 2 to 10 keV polarization degree as a function of the cosine of the inclination angle. So it's I chose 2 to 8 keV because it's the energy band of the X-band, and from bottom to top is the increasing Lorentz factor of the cornea. So what you see here is that if the cornea is moving at relativistic velocity, then the polarization degree can be very high, to around like 30%. And there is a trend that the polarization degree is increasing with the velocity of the corona. So again, we can use the polarization observations to constrain the dynamics of the corona. So that was for the black hole boundary, and now I will talk about the AGN. So in a submitted paper led by Francesco Rossini, we modeled the X-ray polarization of this AGN MCG 52315. So why this one? Because it's a X-ray bright one and it's Compton thin, and it's one primary object of X-pair. So the observed X-ray spectrum, it showed that it has a photon index of 0.8, 1.8 to 1.9, and a energy cutoff between 100 and 200 keV. So similarly, we assume three geometries: the spherical one, the slab one, and also the conical one. And we tried three different values of photon indices: 1.6, 1.8, 2, just to take into account the uncertainties of the photon index. And then for each photon index, we assume three different kernel temperature, and to take into account the uncertainty of the cutoff energy. And for each temperature, we adjust the value of optical depth to reproduce the assumed photon index. So what we found is that so here from left to right is extreme Kerr black hole, and then non-spinning black hole, and non-spinning black hole, but with truncated disk. And for each subfigure, there is the polarization degree as a function of the cosine of the observer's inclination. So what we found is that if you look at all these subplots, the polarization degree decrease with the inclination. So it's the same with black hole X-ray boundaries. And then if you compare figures on the same row, then you see that the polarization degree for a Kerr black hole is larger than a non-spinning black hole. So this is again similar with the case of black hole X boundaries, that the polarization changes with the black spin. So potentially we can measure the black spin in AGNs with X-ray polarization observations. And this figure shows clearly that the polarization degree is sensitive to the current geometry. So again, it's a polarization degree in the 2 to 8 keV band as a function of the cosine of the inclination angle. And the red one is the spherical corny. The dashed dotted line is the conical one, and then the dashed line is the slab one. The shaded area is the measured inclination of the source, and the gray dashed line here is the sensitivity of X-path. So you can see clearly that in this inclination angle range, X-path will be able to tell the geometry of the corona. So to summarize my talk, we know that the X-ray emission of agents and the hard state X-ray binaries from the X-ray corona, but there are lots of properties of the X-ray corona we don't know yet, and the X-ray polarization will provide additional information and will break degeneracies. So with our Monte Carlo radiative transfer code, we modeled the X-ray polarization of this accreting black holes of both stellar mass and supermassive black holes, and we found that the polarization degree is sensitive to the geometry, the spin, and also the dynamic of the corona. So thank you for your attention.